So the next talk is by Aman, and he will tell us about QCD thermodynamics for nuclear models.
I'll be talking about nuclear models, which are written at high densities, and what they can tell us about the thermodynamics of quantum chromodynamics. So if you look at the phase diagram of quantum chromodynamics, in the title I have written conjecture because a lot is not known about this phase diagram. In this figure, on the x-axis we have the baryon chemical potential, or equivalently the baryon density, and on the y-axis we have temperature. Both are in the units of MeV. So most of our knowledge about this phase diagram comes from lattice QCD. So at low baryon densities, close to 0, we know that the transition from a confined hadronic phase to a deconfined coagulon plasma phase is a crossover transition, and it happens at nearly 156 MeV. As we move towards higher baryon density, we find that we expect that the transition should change from crossover to a first order phase transition. However, we do not know where this line lies. We do not know where the critical endpoint lies, at what baryon density. If we go to still further baryon densities, at low temperature and high μb, we have a little bit idea from the neutron star physics studies, but again we do not know at what baryon chemical potential or the baryon density the transition from confined to deconfined phase occurs. We also don't know what the state of the ground, the phase of the ground state is, whether it is a color superconducting state, some inhomogeneous state, or something else. So most of our knowledge is limited to low baryon densities from lattice QCD and also some collision experiments, and also a little bit to the low T, low temperature and high μb region from neutron star studies. Of course, the fundamental QCD Lagrangian is known, but even so, one cannot do the calculations so easily. So in such a scenario where it is difficult to make calculations from first principles, we use what are known as models, hadronic models. So these hadronic models are basically some Lagrangians in which the degree of freedom is are the hadrons, the baryons and the mesons. So these models are written keeping some particular region of the phase diagram in mind. For example, one such model is hadron resonance gas model, which works well at small baryon densities near the temperature axis. And on the other hand, we have some nuclear mean field models which work well at high baryon densities and low temperatures. So before I move on to the nuclear models, I will talk a little bit about the hadron resonance gas model. So in this model, one has a system of baryons and mesons, which are known from lattice QCD and some quark models. It contains both stable particles and resonances, but otherwise it does not contain any interactions. Resonances are attractive in baryons. So through the inclusion of those resonances, the model has some attractive interactions, but otherwise it is a free collection of the baryons, mesons and resonances. This hadron resonance gas model has had some successes. For example, if one looks at the pressure of the hadron resonance gas model at 0 baryon density and compare with lattice QCD, one finds a very good agreement up to the critical temperature. Also, the hadron resonance gas model has been successful in predicting the yields of the different baryons from a thermalized system. But it also has some problems. One is that the model does not incorporate chiral symmetry and its restoration. Chiral symmetry is an important and known aspect of QCD, but it is not included in the model. And because chiral symmetry is not included, one cannot study the effect of the critical modes. So if you look at this phase diagram, if the critical endpoint exists, then in that case, one expects certain fields to become massless as one comes closer to the critical endpoint, and it is expected to have experimental signatures. But because chiral symmetry is not included in HRG model, one cannot study the effect of these critical modes. One more thing, in this phase diagram, at low temperatures and baryon densities, we know that the system is made up of hadrons. And if the system is made up of hadrons, one should have a universal hadronic model which works well both at high densities and at low densities, because one doesn't expect the interactions to be different in different regimes. So keeping this in mind, some people have applied HRG model at high densities, but it is now known that the result it gives are in contradiction with known facts at high densities. Another important problem with the HRG model is that it does not have repulsive interactions. So if you look at this plot, this has been taken from Hot QCD 2020 paper. On the y-axis, one has the second derivative of pressure with respect to baryon chemical potential. And on the x-axis, one has temperature. If one looks at the magenta line, which is the HRG result, and compare it to the green line, the gray line, which is the continuum lattice result, there is a reasonable agreement up to Tc, which is represented by the yellow band. However, if we move on to the fourth order derivative of the pressure with respect to baryon chemical potential, and now compare the magenta line with the gray line, one finds there to be significant differences not only at Tc but also below. So hadron resonance gas model clearly fails in explaining these derivatives of pressure as seen from the comparison. So the question is, what is the resolution? This is a plot from paper by Guru Prasad et al. In this, again, the authors have plotted the lattice QCD data given by the points and error bars. The purple line is the HRG result without any interactions, and the green dashed line is HRG result by including the repulsive interactions. So as seen from the plot clearly, the inclusion of the repulsive interactions improves the agreement with lattice greatly. So this comparison of HRG and lattice tells us that the repulsive interactions are important in any hadronic models, but are not present in the original HRG. Now we come to nuclear models. So these models, these Lagrangians are written keeping in mind the physics of high density, and the degrees of freedom are much fewer compared to the HRG type models. So the degrees of freedom in this case are represented by psi, which represents proton, neutron, and possibly some strange baryons. Then there are the interaction terms mediated by sigma and the omega meson. Sigma meson is responsible for the attractive interactions, while the omega meson is responsible for repulsive interactions. And as we just saw, the repulsive interactions are important in explaining the properties of thermodynamics of QCD. So the idea behind the present study is to solve these models at high density and extrapolate those results at somewhat intermediate densities, and then compare it with the lattice results and see how good the agreement is. If the agreement is good, then it shows us that the models, the hadronic models have somewhat universal character. They can explain both high and low density physics. While solving these models, one must also keep in mind some constraints. For example, in heavy ion collisions, NQ by NB equal to 0.4 is related to the charge to baryon density ratio in the colliding nucleus. And the other constraints such as mu q equal to 0 and mu s equal to 0 are just convenience, because the calculations are somewhat easier in this case. So now we come to some results. So here in this plot, we have the value of the mean fields, basically how much the omega and the sigma are contributing as a function of the baryon density. So the red ones represent the omega field and the green one represents the attractive sigma field. The sigma field is proportional to the scalar density, which is always non-zero, and hence even at mu b equal to 0, it has a non-zero value. The omega interaction, the repulsive interaction, is proportional to baryon density, and therefore it goes to 0 as mu b goes to 0. And as seen from the plot, it is clear that both the attractive and the repulsive interactions are important at finite mu b. So this is one of our results. In this plot on the y-axis, we have the fourth order, the ratio of fourth order to second order derivative as a function of mu b. The green band is a result from lattice QCD for this result. The plum colored line is the hadron resonance gas model result without any interactions, and the orange line is a result from the nuclear model. As one can see clearly from the plot, there is a significant difference between the non-interacting HRG result and the nuclear model result with finite interactions. And the nuclear model result also matches with the band from lattice QCD. In this plot, we have a third order derivative with respect to baryon chemical potential, but also a first order derivative with respect to the strange chemical potential. Because of this strange chemical potential derivative, the majority of contribution to this plot comes from only the strange baryons. The light green colored band is again the lattice result, and plum colored line is the non-interacting HRG result. The orange result is from the nuclear model. In this case, we find that the orange result doesn't match with the light green color band. This is most likely due to the fact that the lattice result, of course, contains the entire hadronic spectrum, including all the strange hadrons. Whereas the nuclear model we have contains only two strange hadrons. It is my expectation that if one includes more hadrons, there can be an agreement between the nuclear model and the lattice for this case also. This plot is also important because it is sensitive to the strange baryons and thus also the strange omega coupling, which is not the case in other plots. So if one can obtain a good agreement between the nuclear model and the lattice, one can also possibly constrain the omega coupling with the strange baryons. Now I come to my final result. On the y-axis, we have temperature scaled by the critical temperature, and on the x-axis, we again have the baryon chemical potential. The green band is the crossover line known from lattice QCD, and the pink band is a result from the nuclear model. Each point in the pink band corresponds to energy density, which is given in the title. This energy density is the energy density corresponding to the crossover transition at 0 mu b. It is known from lattice QCD that at small baryon densities, the crossover line and the chemical freeze-out line coincide. In our study, we have assumed that this thing happens at a constant energy density, which is given in the title. In the study, we have assumed that this thing holds at finite mu b as well, that the crossover line, the chemical freeze-out line is also a constant energy density line at high densities. So assuming that the pink band should represent a chemical freeze-out line at high densities. So if this is the line of chemical freeze-out, any phase transition should happen only at a higher, above the band. From the lattice QCD, it is also known that T by T naught for the critical endpoint lies below a value of 0.85. If it lies in a range of 0.8 to 0.85, then we get the gray band. And from the intersection of these two bands, one can put a lower bound on the location of the critical endpoint. So now I will summarize. From our study, we have found that for many of the results, the high density data extrapolated to low baryon densities does match the lattice bands. As one can see in the plots, the lattice bands have quite a width, and if one has a more precise data in future, then that can, so one can make a more precise statement from such a study. Model is of course limited due to the lack of degrees of freedom and also the lack of knowledge about the couplings. At low densities, the repulsive interactions rapidly go to 0. So the mean field first order result, since it is 0, it is important that at low densities we have a beyond mean field calculation. And by combining hadron resonance gas and inputs from nuclear model, one can perhaps build a more universal hadronic model which works both at high and low densities. And the way these models are written, they can in principle be modified to include chiral symmetry, and one can then directly study the critical endpoint within the model.
Thanks, Aman, for your talk.